Hi again, everybody. This is our third video on using integration to find volumes. In this video, we're going to start by taking a region between two curves and rotating it around the x-axis. This is going to again give us some sort of solid, and we're going to want to find the volume of that solid. Okay, so let's get started. So if I want to rotate this around, let me try to copy g of x and f of x, only we have to flip them upside down here. So first let me do the g of x, and okay, something like that. And then I'm going to try to copy the f of x. So let's see, that's going to start down here a little bit, and we'll get a little further away and then come in and like that. Something like this. Okay, what am I trying to get at with this here? Well, okay, when I rotate this region, of course, I'm also rotating f of x. So it ends up down here, g of x ends up down here, and then of course it keeps on going all the way through. So let me just try to draw in green here what is happening with the f of x. So there's the beginning, there's the end. And now let me try to do the same thing, but with g of x. So I get my beginning and my end. And, well, maybe let's draw one down the middle here. So if I pick some point here on f of x, it comes down and dotted in the back, and then we'll do it for g of x in the middle. Okay, so this is rotated around. And the big idea is, because when I rotated, I had this region, which was, there's some distance between that region and the x-axis. When I rotate it around, I get this hole in the middle. Yeah, you could fill it with, some cheese or something. Quite nice. Okay, so there's this hole in the middle, and when I compute the volume, I don't want that hole. Now, it's pretty easy to get rid of it, because make the following observation. If I rotated f around, I didn't even think about g, I just rotated it around and computed the volume, well, that would give me this entire region. On the other hand, if I forgot about f and rotated just the g around, the solid I would get would be exactly the whole. Now, if I want to find the volume of the whole thing minus the whole, then I should just find the volume I'd get by using f of x, which gives me the whole thing, and subtract away the volume of the whole, which is what g of x gives me. Now, in the last video, we saw exactly how to compute those sort of volumes. So the volume that I would get from the f would be, well, you integrate from a to b, and then we have pi f of x squared dx. But now I want to get rid of the whole. So we're going to subtract what we get by rotating the g of x around. So again, we integrate from a to b, but we now have pi g of x squared dx. And of course, we can put this together into one integral, and we often will. So of course, I have a pi in each. I can pull that out. Integrate from a to b, and now I have f of x squared minus g of x squared dx. So it's important to be able to set this up already with the f of x minus g of x. This should remind you of the area between curves video though, right? Which one of these comes first matters. And of course, we want the one which is giving you the bigger solid first, because we're subtracting out the smaller solid. Okay? The downside of this representation isn't that it's wrong, it's perfectly correct, but you lose a little bit of the intuition. Right? The intuition here is I'm taking the big solid and I'm subtracting out the smaller solid. Big solid minus smaller solid. Okay? Ultimately, you got to feel comfortable though, so you can use either one of these. That's fine. Okay. What happens now if instead of going around the x-axis, I want to go around some other axis? All right, so I'm going to clean up and we'll try that next. And welcome back. So I have a completely different picture up here now. Actually, it's almost exactly the same picture, but I've changed the axis. It's no longer the x-axis. It's now y equals c, where c is, well, any constant. Could be 3, could be negative 17, I don't know. And I want to know how this is going to change the volume. The answer is not a whole heck of a lot. when we want to compute the volume of, say, one of those individual cylinders, so say I took this little circle and extended it out to a nice cylinder, and I want to know the volume of that cylinder, the key is that I need to know the radius. So if I want to know the radius, I just need to know the distance between the curve, which is g of x, and the axis of rotation. Before that happened to be y equals 0, the x-axis, but it doesn't really matter. You just need to know this distance, and now instead of being the difference between g of x and 0, it's the distance between g of x and c. And so if I want to know the total volume, it's actually not going to be a whole lot different. I'm still going to say, well, I want the bigger volume first, so I'll integrate from a to b. Pi, well, it used to be f of x squared. Why was it f of x squared? F of x was the radius. Why was f of x the radius? It's because that was the distance between the x-axis, which is y equals 0, and f of x. But now, if I want to know, so let's draw a nice, a nice cylinder in here. There's our cylinder. If I want to know the distance between the axis of rotation and the function, well, the axis is now c instead of 0. Function is still f of x, and so the difference is f of x minus c. That's the radius of my cylinder. Of course, I can't just write the radius, I have to square it also. So we get a square here, and we still have dx. Okay, and then we're going to subtract out the tasty filling in the middle. So we're going to subtract out, and now we have the integral from a to b, pi. Well, again, we're now looking at the distance between c and g of x. So that's g of x minus c. And then I need the square of, well, remember, this is the radius. And the area of the base is pi r squared. And then we have dx. Okay, so it's a small, subtle change, but it's an important one. We have to always look at our picture and say, okay, when I'm computing the area of that base, I need to know the radius. And that radius is not just f of x squared. It's the distance from the axis of rotation to the function. Okay, so subtle difference, but it's going to make a difference in our formula, at least a subtle one. All right, so I'm going to clean this up a little bit, and we'll do an example. Okay, so in this example, we've drawn two different curves. We have g of x, which is x squared, and we have f of x, which is 2x. Now, it's kind of strange. 2x looks like it should be the smaller function, but we're going between, well, let's see, where do these intersect? Where does x squared equal 2x? Let's see, divide by x, you get x equals 2, right? And, well, why wouldn't we be able to divide by x? Because x was 0. They intersect there too. So they intersect at 0 and at 2. And in between 0 and 2, 2x is actually the larger function. So there's going to be some region in between them, and I want to take this region, and I want to rotate it around, say, the x-axis. Okay, fine. If I want to rotate it around the x-axis, I want to get my volume. And how am I going to work this out? Well, I'm integrating between 0 and 2. And then I need pi. Well, we can always pull the pi out. I need the larger function, the one that's going to give me the big cylinders. That's my 2x. And I need to square it. All right, why? Because that was going to be the radius. All right, when I draw this around, I get a radius 0 to 2x. Subtract. Now I need the GUI inside. That's my x squared. But remember, you have to square it. Okay. I guess those should be circular parentheses. Okay, and then times dx, all right, which is off the screen. This is not starting well. All right, take 2. Okay, so in this example, I've drawn 2 functions, f of x, which is 2x, and g of x, which is x squared. And I've taken the liberty of figuring out where those 2 functions intersect. It's at 0, and it's at x equals 2. Once I know that, I know if I want to compute the volume that I get by taking this region in between the 2 and rotating it around, well, in this case, just the x-axis, then the volume is going to be given by taking, well, let's do the big function first. That's the 2x. I integrate from 0 to 2 pi times my f of x, which is 2x squared. And then I'm going to subtract the GUI inside, which I get from the smaller function. So I integrate from 0 to 2 pi, and now my function here is x squared dx. Okay, not so bad. What if we change this axis of rotation? How's that going to change things? So let's say, well, let's move this axis down first. So say I want to change my axis of rotation so it's no longer going around the x-axis. Well, I guess that's fine to leave the circle there. But now let's say it's going to be, well, okay, I guess this is why we want to switch this. Back it up. Okay, so now let's say, though, we don't want to go around the x-axis, but around some other axis of rotation. So say I want to rotate down here. Say this is going to be y equals -3. Okay, so I have y equals -3, and I'd like to rotate no longer around the x-axis, but now around y equals -3. How is that going to change things? So when I build my cylinders, they're going to have a larger radius now. The distance from f of x to the axis of rotation is going to be increased. By how much? Well, whatever this distance is. Well, how far is it from the x-axis to y equals -3? The answer is 3. All right, that's where this hits, -3. And so all the radii are going to increase by 3. So I would need to go back. I would need to go back here, and instead of it being 2x, right, that was the original distance to the axis of rotation. So this is 2x. There's now an additional distance of 3. And so I could put here 2x plus 3, and of course I still need to square it, dx, and I need to adjust g of x in the same way. So instead of x squared squared, I'll have x squared plus 3 quantity squared. Okay, so that's not so bad. What if we move the axis of rotation up above the graph? How would that change things? So say I wanted to move it up here. Okay, so maybe this is y equals 6. So that's sufficiently big. All right, well, now when I'm rotating, the axis of rotation is up here. Notice something really funky happened. F of x is no longer going to give you the big cylinder, because when I rotate around this axis, that's actually a smaller distance than when I rotate g of x around this axis. So this is something you have to look out for. It means, well, okay, we're going to have to erase these. They're going to be in reverse order. The g of x part is going to come first, then the f of x. So let's see what happens. We're going to first integrate from 0 to 2, and we know it's going to be pi times the radius. So the radius is the distance between the function and the axis of rotation. Okay, so here's my function, say at some point, and there's the axis of rotation. That's g of x, that's 6. So the distance is going to be, well, since 6 is bigger, 6 minus g of x. 6 minus g of x, right? G of x is x squared. So that's actually what needs to go in here. 6 minus x squared squared dx. Okay, and then of course I need to do my, I need to, not add, but I need to subtract out the GUI center, which is now supplied by the f of x instead of the g of x. So we integrate from 0 to 2. We have pi. And again, I need the distance between the line, the axis of rotation, and f of x. So that will be 6 minus 2x. And then we square that radius. All right, so there's all sorts of ways we can move this line around. But if you stick very close to the idea that we just need pi times the square of the radius, where the radius is the distance from the axis of rotation to your function, you can't go wrong. You do need to be careful, though, which is going to be further away from the axis of rotation, right? When we switched over to the 6, the green was no longer further away. That became your GUI center, right? And we always subtract out the GUI center, as tasty as it may be. All right, we'll see you next time.